Lesson 2 of industrial instrumentation, I will discuss basically the dynamic characteristics of instrument or sensor. Now, one thing I told you that sensor or instruments, we are rather using very loosely here the term, because sometimes we call it sensor, sometimes we will call it instruments as such. When I will call the second order instrument or first order instrument, it does not necessarily mean only instrument as a whole, it may mean also the sensor. Now, the contents of this lesson are dynamic characteristics, zero order instrument, first order instrument and its responses to step input, to ramp input, to sinusoidal input. You see, in both the cases, in the cases of first order and second order instruments, we will consider these three different inputs and we will compare putting these side by side. At the end of this lesson, the viewer will know the characteristics equation of an instrument, zero order instrument and its example of some zero order instrument, first order instruments and its responses to step, ramp and sinusoidal input. In the instrumentation system, you will find that most of the time we will face these three different inputs. Even though ramp input is not very usual, we will find instead of ramp the input will be sinusoidal input. However, we will consider the ramp input also, and sinusoidal input is very common, like ambient temperature variations or in some biomedical applications we will find this type of inputs will be there. Step input is very common in the electrical system, because suppose you are using a voltmeter, you are giving the input to the voltmeter, this is considered as a step input. And also we will consider the error in the measurement, how much the error, because until unless you know the error, you cannot reduce it. What are the factors on which this error will depend? We must know that thing, and how the errors will behave as the time grows, that also we should know. For that reasons, we should also consider error in the measurements in all the three different inputs, and physical parameters that influence the errors that I told just now. Now, if I look at the dynamic characteristics, the dynamic response of an instrument to a signal input may be described by the nth order differential equation such as following. It looks like nth order derivative of y with respect to t plus n minus 1, n minus 1th derivative of y with respect to t, so on until it is a1 multiplied by dy by dt plus a naught y equal to b naught x, where y is the measured quantity or value indicated by the instrument, right. X is the input quantity. For any measurement systems or sensor, we will actually want that the whatever the x, y should show that without any time delay, without any phase lag. But this will not happen. You will see that there will be some lag in the system, there will be some delay in the system. Okay. T is the time, and where a naught, a1, a2, so on up to a n and b0 are the constants which are the combination of the system physical parameters. What is the meaning of the system physical parameters? Suppose I have electrical circuits that R and C will be the, suppose in the case of, electrical circuit R and C will be the factors which will depend. Suppose I have a circuit like this, I have a simple electrical circuit. So, I have a resistance, capacitance. So, if I draw, so the value R and C value, so the physical constant will depend on the value of R and C. Now, here I will show you a block diagram of a measurement system. So, I have an input quantity xt, I have an output quantity yt, and I have some initial conditions. These are necessary, these initial conditions are necessary to solve the differential equation. In the case of first order instrument, it will be first order differential equation. Now, zero order instrument is the simplest instruments we have, but there are some instruments, also some sensors that which are zero order in nature. The simplest model of a measurement system is a zero order differential equation. It looks like this: a naught y equal to b naught x, or y equal to b naught by a naught x multiplied by x equal to k x. You see, if you go back to the our initial differential equation, it will look like you see this is our differential equation. So, these differential equations, nth order differential equation, if you put all 0, that means from a n up to a 1, that means a n minus 1 up to a 1, if you put all equal to 0, I will get the zero order instrument which looks like this. That actually I have shown just now. So, only this part if you take, it is a zero order instrument, right. So, this is our zero order instrument. You can see here y output equal to b naught by a naught multiplied by x or equal to k x, where k equal to b naught by a naught. I am sorry, this will be b naught by a naught, and k is called the static sensitivity of the system. K is called the static sensitivity of the system. Static sensitivity has a lot of influence. You will find the calibration curve of the entire system will depend on the static sensitivity. Remarks, you will see that it is obvious that x may vary with time, however, the instrument output follows it perfectly with no distortion or time lag. Whatever the input in the system, it does not matter, it will immediately appear at the output without any phase lag in the system. So, that is a zero order instrument. It does not matter what is the input, it might be step input, it might be ramp input, it might be your sinusoidal input. So, immediately it will appear at the output without any lag, without any phase change. So, that means it is a zero order instrument. Now, in zero order behavior, the system output is considered to respond to the input signal instantly. The static sensitivity is found from the static calibration curve of the measurement system. It is a slope of the calibration curve. How does it mean? It means that if I look at, it will be, suppose I have this characteristics calibration curve, this is x, this is y, and I have a linear relation like this one. So, slope of this calibration curve, okay, that means dy by dx will give you the static sensitivity. So, this will give you the static sensitivity, and since it is linear, you see that anywhere the value of dy by del y by del x. So, if it is del x, it is del y, it is same. Now, I will take an example of a potentiometer. Potentiometer is a very important sensor. You will find in all electronic circuits, also in instrumentation you will find it is used as a position sensors, rotational positions, linear positions, for all these different reasons it is used. And in the electronic circuits, potentiometers are extensively used, whether you call it potentiometer or you call it preset or you call it rheostat, all are same. These are basically potentiometer. Potentiometer 3 terminal device, you see here, This is our potentiometer, you can look here. So, I have a supply excitation voltage I have given and total angular rotation of the potentiometer, because if you look at the physical shape, it looks like this. I have the potentiometer looks like this, is not it here. So, I have a wiper or jockey in the case of potentiometer or preset we call it wiper, in the case of rheostat we call it jockey, but the principle is same, both are the 0 order instruments. Potentiometer is used in the electronic circuits and rheostat is used actually in the case of electrical circuits, and presets are used for, it is not for multiple use, but for limited number of use. If you use 1 or 2 or 3 times, you can use preset, which is basically nothing but a low cost potentiometer. So, I can say the rheostat, potentiometer and the preset are basically same. So, you see here the total rotation is theta t. So, I can have any position theta. So, I am giving the voltage, battery voltage here connected here. So, this is my E, right, and I can measure this voltage between this point and this point, that will be my output voltage E naught. So, this can be E naught, right, this can be my E naught, clear. So, this will give you the so total is theta t. So, this will give the schematic view of a potentiometer. A potentiometer is the example of a 0 order instrument, and its equation looks like E naught equal to theta by theta t multiplied by the supply voltage or excitation voltage, which is equal to k theta, where k equal to E by theta t, which is volts per radian, because E is a constant, it does not depend on the position of the potentiometer. Theta t is the total angular, these are constant for a particular potentiometer, you know this is constant, that is k equal to E by theta t, which is volts and radian, and this is the static sensitivity of a potentiometer. You can see here that the potentiometer, that it always should whatever the input it will get, immediately it will be shown at the output without any time lag or without any phase change. That actually happens in the case of potentiometer. That means whatever the inputs you are giving, it immediately appears at the output. I can use it as a position sensors also, because as you can see the output voltage is directly proportional to the position. What is that position? If I go back, I can see here. You see here that output voltage is directly proportional to theta. So, E is a function of theta, so which can be utilized to make a position sensor, and it is a 0 order instrument. So, obviously, there is no phase lag or no time lag, phase change or time lag in the input output. Okay. Now, next we will consider a first order instrument. The transducer that contains the storage element cannot respond instantaneously to change in input. The mercury in glass thermometer is an example of a first order instrument. The bulb takes energy from the environment until the two are at the same temperature or steady state condition has been reached, right. The temperature of the bulb will change with the time until the equilibrium is reached. The rate at which the temperature change with time can be modeled with the first order derivative, and the thermometer behavior is modeled as a first order differential equation. Therefore, the dynamic characteristics of a first order instrument is given by, looks like this, A1 dy by dt plus A naught y B naught equal to B naught x. This is similar, you see that if you remember our nth order differential equation, that A n then d n y by dt n, all those things, if you put all the coefficients from A n to A 2, from A n minus 1, so on A2 equal to all 0, I will get a first order characteristics equation of a first order instrument. So, exactly we got that thing, you can see here. So, A naught, so you can see here. So, that is we have multiplied entire equations by A0, I got the equation A1 by A0 y dot plus y equal to B naught by A naught into x. So, dot we just replace dy by dt. So, tau, now I replace A1 by A0 equal to tau, tau y dot plus y equal to B naught by A naught upon A naught x. Finally, we have written tau y dot plus y equal to kx, right. K we remember for the 0 order instruments also, k is the static sensitivity of the system and tau is the time constant of the system, and this is the equation number 1. Where tau equal to A naught upon A0 and k equal to B0 by A0. Obviously, all this time constant of the system, like as you told, because if you take an example of a thermometer, this A1 upon A0 and static sensitivity B0 upon A0 depends on some of the physical parameters of the system. What are those physical parameters? That means what is the size of the bulb of the thermometer, materials which you are using as a thermometer liquid, all this factor will actually tell you the value of the tau. If I use for an example, just from intuition you can tell, if you take a large bulb, so that if I have a large length of the mercury, so in that case I can use the time constants of the system will also increase. Similarly, the k also will be actually controlled by the physical parameters of the system. And if you remember our the nth order differential equations, we have written there clearly this value, that means A0, A1, B0, all are the basically physical, depends on the physical parameters of the system. Tau is called the time constant of the system, and it always has a dimension of time, quite obviously. Now you slowly consider one by one the inputs. Now first I consider the step input. Now step input is very common to the system, especially in the electrical systems. Step input is very common. Step input function is defined as x equal to 0 for t less than 0 and x equal to xs for t greater than equal to 0. This is equation number 2. This set of equations we have given the equation number 2. These are necessary to solve the differential equations, right. So, how does it look? It looks very simple. It looks like that my input, if I time axis, if I plot, see it looks like this, then suddenly it goes, this is my input. If I take different colors, well, it will more. So, it will, my input looks like this, it go like that. So, this is our 0, that means at t less than 0, it is x equal to 0 and this is our x, and for t greater than 0, x is a constant, xs. Xs actually I want to signify the steady state value, because this will be our steady state value of the input. I want my output will be always exactly equal to xs, because if it is the xs, I can steady state value, right. Now substituting in equation 2 in equation 1 for t greater than equal to 0, we get tau y dot plus y, tau y dot plus y equal to k xs. I have given the equation number 3. The solution of this differential equation, equation 3 keeps for t greater than equal to 0 equal to y equal to k xs 1 minus e to the power minus t by tau, right, very carefully. So, e to the power minus t by tau. These are laws of significance, the meaning of this, and k xs. As you can see that as the time grows, what will happen to this, that as the time grows, this is the transient part, this will die out. So, ultimately you will find that the output will follow the input, because at that time this will be y equal to k xs into 1. this becomes 0. So, this equal to 1. This means that the whatever the static sensitivity multiplied by the steady state value of x will be the output, right. But you will see here that this tau carries a lot of lot of influence at what time you will get that y will be equal to kxs. If the tau is large, it will take long time to die out. If the tau is small, it will take a very quick time that it will reach the final steady state value. Output will reach the final steady state value, because it is minus term is there. So, let us play it, so that this we have done in flash. So, it will be better, it will look like this. X axis is my input, y is my y axis is my output, y by kxs. Now, interestingly, you see one thing, I have normalized it, because this is very much necessary. Okay. Let it finish, then we will start again. Hopefully, it has finished. Now, see here that I have taken, this is my y by kxs. I have taken normalized value. So, y will be the unitless quantity. So, since it is normalized, so it is unitless, right, and this value, maximum value will be always 1, since it is normal 1.0. 1.0. So, this will be always 1, and we have plotted t in the x axis. As you can see that as I increase the value of the tau, it is taking longer and longer time to reach the final steady state. This is our final steady state value. So, as I increase the tau, so I will get more and more time. So, I can have, if I still further increase the tau, so it will go like this. Suppose I have one of the example of this, that suppose I have a thermometer. Thermometer has a simple mercury in glass thermometer, fine. It has some, depending on the type of liquid which you are using, the type of the thickness of the glass and all those things, it will have some value of the tau, because physical parameters will control the value of tau. Now, what will happen, you see here that if I for protection, suppose that mercury in glass I put on a steel sleevings, that means I have a mercury in glass manometer, mercury in glass thermometers. So, I put on a, for protections I put on a sleevings, so that it will not break. So, in that type of situations we will find that the time constant of the system will increase. Later on we will see that we have a various types of thermometers. We have thermocouple, we have thermistor, we have RTD. You will find that in the case of RTD, because of its large huge size, we will find that it is the time constant of the system is very large compared to the thermocouple or thermistor. So, time constant will control that how quickly your output will reach the input. So, in this case you will find that the tau increases, that means your time constant increases, right. Error in measurement at any instant of time is defined as EM. We have used the subscript m, that is to tell that it is error in the measurement, x minus y by k. So, it will be ultimately xs minus xs multiplied by 1 minus e to the power minus t by tau, and it is for a step input, equal to xs into e to the power minus t by tau. We have seen that, you see that as the time grows, so this error will be smaller and smaller, because it is exponential term and there is a negative. So, obviously, as the t will be large and large, so this will die out. At the initial stage when t is 0, so it has a large value, it is value almost equal to, it is exactly equal to the xs, the steady state value. As the t grows, so it will die out. So, it will be better visualize if we run in a flash. So, the normalized error, if I normalize, if you make it unitless, so it will be EM by xs equal to e to the power minus t by tau. It will be better visualized, I mean in a flash. It will, you can see here. So, x axis we have plotted t by tau instead of t. It does not matter because it is a normalized, we have because t is a dimension of time. So, we have plotted normalized value. It does not matter because it is t is just multiplied by some constant factor of 1 by tau. You can see here that at a very low value of t or at very low value of t by tau, or when it is 0 initial state, we have just given the step input, my output is maximum. This is our error is maximum. So, as the time grows, so obviously the error will fall down. So, exponential decay, you will find as the time goes, so my error will get decreased, or the normalized error is getting small and small, and ultimately it will die out. So, this is very important in the sense you will find that in the system that you must know that when the error will die out. In some cases I cannot, my entire reading will be erroneous because of from a sensor, the reading from a sensor, because if I take reading, suppose if I take the reading of the sensors after 1 of t by tau, so it is totally error. So, I cannot accept, I should take the reading when the t by tau is 4 or t is 4, when 4 seconds, suppose if it is, if it is, if I plot it in terms of t instead of t by tau, or suppose tau is 1, so after 4 seconds I should take the reading. Now, we should consider the ramp input. Ramp input is not very usual. I mean, in the instrumentation system, it is very difficult to give a ramp input, but electrical system is very necessary. You will find in some of the cases you have to give the ramp input. One of the good example of the ramp input is the Sawtooth waveform. So, you are aware of that in the case of always in the, this is a Sawtooth waveform you give in many electrical circuits, this type of waveforms. One of the common example of the Sawtooth waveforms when we give in the oscilloscope, in the cathode ray oscilloscope to measure some voltages. Voltages amplitudes we are giving between the plates y, particle plates, and the Sawtooth waveforms we are giving in the x plate, so that to synchronize or to make the wave stationary. In instrumentation system, Sawtooth, ramp input you will find it is not very usual, even though we consider the ramp input. In many cases, we will find that instead of ramp input, the input which I will give is basically a terminated ramp input. In the case a step input also sometimes very difficult to give in a instrumentation system. So, it will appear actually the terminated ramp input like this one instead of step input. So, in this case the must consider these portions which looks like a ramp. Okay. So, for that reasons we considered here the ramp input. Now, the ramp function input is defined as x equal to 0 for t less than 0 and x equal to x s dot into t for t greater than equal to 0, right. It looks like this, that it is a time varying. So, it is going on increasing like this, right. This is t. So, this is at any step time what will be the value of x that can be multiplied by t. So, this is our x s dot, slowly it is increasing, right. So, this is our ramp input. Recalling the characteristics equation as equation 1 of the first order systems, we call that first order systems here. We just replace x by x s dot t, x s dot means dxs by dt into t. So, tau y dot plus y equal to x s dot into t. This is our first order differential equation for ramp input. We will solve this equation and see how the output will come, how the response will come, and how my error in the measurement system will come. The initial conditions are x equal to y equal to 0 for t equal to 0. That is quite obvious. That means, if I assume that the ramp input, it does not matter that if I give a input like this one. So, at t equal to 0, So, quite obviously I can say that the x is equal to 0 and y is equal to 0, and my output will look like y equal to k x s dot tau e to the power minus t by tau plus t minus tau, right. Now, error in the measurement at any instant of time will be given by C em equal to x minus y by k x s dot into t minus x s dot tau e to the power minus t by tau minus x s dot into t plus x s dot into tau equal to minus x s dot tau e to the power minus t by tau plus x s dot into tau, right. Sorry, let us go back. So, this is our you see there is two part, one is the transient part and there is a steady state part. Why it is transient? You see that this, as the time grows, this function will going to reduce as the time goes on. So, this will become almost approaches to 0, but this will remain as it is. So, this is our steady state error and this is our transient error, right. You see, if I plot it, it will look like this, that steady state error at any instant of time, okay, hopefully it is finalized, it looks like this. So, x axis we have plotted time and this is our output, these I have plotted, this is my input. So, this equal to actually x s dot into t, right, and this is y by k. I have plotted the output. Actually, this should be parallel. I mean, it's I cannot draw it nicely. So it should be like this. It should be parallel to the input. Here, the steady state time lag you can see. It is the steady state time lag of the system. Initially, time lag is very small, but as the time grows, we have a steady state time lag, which is tau. And steady state error also you can say at the initial stage, steady state error is very small. Why? If you look at, if you go back. If I go back to the previous slide, you see here we have a negative term here. So, that will contribute. So, this will become almost 0 for some value, and as it grows, as the time grows, so this will become insignificant. So, this will be predominant. That is the reason we got the characteristics like this. Error characteristic, this is my output and this is my input and this my output will look like this. So, error initially is very small and as the time goes we have a steady state error, which is x s dot into tau. And interestingly, you see the steady state time lag is always tau. So, it means that steady state error will be at any step of time, any instant of time is x s dot into tau and steady state time lag is tau. So, what is the remarks of a, I mean for a system with a step input? It is apparent that the smaller the value of tau, the faster will be the disappearance of the transient error. This is everywhere I found that if in the case of step input also you will find that if the tau is small, so I will get immediately I will reach the final steady state value. If the tau is large, it takes long time, right. So, long time means what? The steady state error will take long time to make the steady state error 0, because our goal for any instrumentation system or any sensor that the steady state error should be 0 as quickly as possible. Now, it is apparent that the smaller the value of tau, the faster will be the disappearance of the transient error. Moreover, once the transient has disappeared, the instrument lags behind a constant value, which is again the time constant of the instrument, tau, that is already we have seen, right. Therefore, it is obvious that the lag of the instrument is dependent directly on the time constant tau. For an example, a temperature sensor having a time constant of 5 seconds will ultimately lag behind a ramp input by 5 seconds. Initially lag will be small, but after some time we will find the lag will have steady state value, so it will be 5 seconds. So, whatever the time constant of the systems, our lag also will be the same. So, the measurement error is directly proportional to the ramp input and time. Okay. This is also very important. We have seen that the measurement error depends on the ramp input as well as the time constant of the system. So, if the time constant is small, the measurement error will be small. If the time constant is large, measurement error will be large. And you see, unlike the step input, this measurement error will remain forever. If you look at in the case of step input, I have a input, I am giving input like this, right, I am getting output like. So, after some time there is no steady state error, this will be 0. But whereas in the case of ramp input, you see here, if I take a white page, in the case of ramp input, so there is always a steady state error, initially small, so it is going like. So, there is always a steady state error, this is our error. So, it will remain forever in the case of ramp input. So, it is, since it is a time varying input functions, right. If low measurement error is required, the instrument must have a low value of the time constant. It is quite obvious. If the measurement error is low is required, it is not necessary in the case of step input and all these things, because ultimately it will reach only time constant will control the value, that means after what time the steady state error will be 0. Whereas in the case of ramp input, if you want to reduce the steady state error, it will be always you have to choose the value of the time constant smaller and smaller. Now, I will consider the sinusoidal input. Sinusoidal input is common, that is ambient temperature variations or in some particular applications like the biomedical applications, you will find that when the patient has infected with a malady of parasites, you will find the temperature usually for the first 2-3 days that at a particular time only the particular temperature appears. So, very periodic. So, ambient temperatures also you will find the daytime there is some temperature, night time some other temperature, and interestingly the time constant of the system is obviously very large, right. So, sinusoidal input we will face a lot like vibration analysis and all those things. You see the periodic signals are encountered in many processes such as vibration analysis, ambient temperature variation, then etc. When a periodic signal such as sinusoidal input is applied to the first order systems or instrument, the frequency of the input signal influences the response of the measurement system. So, the frequency will control the lot of parameters we will find that. So, frequency is of prime importance in the case of sinusoidal system. The sinusoidal function is defined as, we can write the sinusoidal function like the x equal to x is sin omega t. Very simple, we all know. That means, if I have a sinusoidal function, so this is my x's. Okay. So, this is total time period t, where t equal to 1 by f and omega equal to 2 pi f, circular frequency equal to f, and t is the total time period and time period 1 by inverse. So, this is the x's value on both sides, this is also x's. So, for t greater than equal to 0 and for t less than 0 it is 0. So, this is our sinusoidal input. So, the characteristics equations will be as follows. Obviously, I have just replaced on the right hand side x by k x s, actually it was there. So, I replaced tau y dot plus y equal to k x s into sin omega t. Initially, our basic equations we remember in the very beginning of the lecture, it is tau y dot plus y equal to k x s. In the case of step input, we have replaced with k equal to x s. In the case of ramp input, we have replaced x equal to xs into t. In the case of sinusoidal input, we have replaced x by xs sin omega t, right. So, the solution to this differential equation yields, ignoring initial condition, that y equal to 0 equal to y 0, get k by xs upon under square root 1 plus omega square into tau square sin omega t phi minus phi, where phi equal to tan inverse omega tau. This we can write as equal to a sin omega t minus phi. Phi is the phase shift of the input signal. There will be some phase shift. That means that if my input is like this, okay, so my output will look like some other. So, it will look like a phase shift like this one, right. So, there is a shift in phase. Sometimes in many instrumentation system, we will find that this phase shift is a nuisance. That means, we have to kill this phase shift. In the case of leading phase angle, we have to use a lag network, and in the case of lagging phasing angle, we have to use a lead network. Even though the circuit is very simple, with one resistance or one capacitance, I can make a lead lag network, right. So, this is my output, you can see here. So, the phase change is coming, and as I told you earlier, you see this omega is very important in the case of sinusoidal signal. That means, omega equal to 2 pi f. What is omega? Omega is, if I draw it here again, so my input signal is like that. So, this is my t total time period. So, f equal to 1 by t and 2 pi f equal to circular frequency omega. So, this omega will influence a lot. It depends on the phase shift, also influenced by both omega and tau. You can see that the phase shift is equal to tan inverse omega tau, and the amplitude of the signal, which is a, which is under k into xs under the square root 1 plus omega square tau square. You will find that if the omega is large, obviously your value of y also will be small, value of a, that means the amplitude also will be small, right. Where a equal to k xs upon under the square root 1 plus omega square into tau square, where a represents the amplitude of the steady state response and phi is the phase shift of the output response with respect to sinusoidal input, right. It is apparent that the amplitude of the output response of a first order system depends on the frequency of the input periodic signal, right. The delay in the measurement is given by d by phi by omega and is expressed in seconds, where phi is the radians. I am sorry, this will be where phi is the radian and omega is in radians per second, right. Now, delay in a system is important. In many cases, we will find we cannot allow delay. In some systems, we will find that we have to accept this delay, because this delay is a natural phenomenon, like a phase shift. It is a natural phenomenon. Only thing we have to make the delay possibly so that the delay will be same for all the frequencies. We cannot make delay 0, but if the frequency for all the frequency range, the delay is same, so that will satisfy our goal. The amplitude ratio is given by a by k xs equal to 1 upon under the square root 1 plus omega square tau square. You can see here. Now, we have plotted here, you see that plotted normalized value of the output, okay, versus omega tau. Instead of omega, we have plotted omega tau. We want to make it also unitless, that is the reason we have plotted. It is dimensionless, omega is in radian per second, this is second, so it is dimensionless, we have plotted. So, this is our response of a first order system, or the frequency response of a first order system, okay, with sinusoidal input, right. So, obviously, since it is normalized, this output will be 1 and this will be 20 log 10 of A by k x s will be 0 dB, right. You can see here that as we increase the frequency, so there is a roll off, and for the first order system this will be minus 20 dB per decade, right. So, this is a roll off and there is a phase. So, the flat response, after that it will start to fall. If I plot the phase, you will find of a first order system with a sinusoidal input, it looks like a phase shift of 45 degree. You see the phase shift of 45 degree at omega t equal to, because you see, you remember that phi phase shift is tan inverse omega tau. So, if omega tau equal to 1, so phase shift will be obviously 45 degree. So, it is 45 degree at omega equal to 1, right, and at very low frequency it is 0 phase shift. As the frequency going high, we have a this omega is high, tau is constant, omega is getting higher and higher. So, if it is infinite, obviously I will get a 90 degree phase shift, right. So, this is about the amplitude and the phase response of a first order system with sinusoidal input. Now, you see this is important because that I told you that earlier that omega plays a key role in the case of response, in finding the response of the first order and second order instruments with the sinusoidal input. So, the frequency will determine, or the tau will determine at what frequency you can use your instrument, because in other way, because if you fix the omega, the tau will be determined, and if you know that my signal has some particular frequency, I can tell that what should be the value of tau for that reason that I will get a reasonable response of the input to the system. Now, remarks will appear like this. It is obvious that both the time constant of the system, and the input signal frequency influence the system response. So, the system response will depend on both omega and tau. We have seen, you see the why, because you see the amplitude also. You remember A equal to k x s root over 1 plus omega square tau square, is not it? We have seen. So, this is my response, or if I take a normalized, so it will be A by k x s equal to 1 upon root over 1 plus omega square tau square. So, as we say that both the time constant of the system and the input signal frequency, which is omega, influence the system response, because it will control the value of the amplitude or the normalized output, as well as the phase shift, which is basically depends on tan inverse omega tau, right. For those values of omega tau for which A by k x is almost equal to 1, the measurement system will have almost no attenuations of the input signal amplitude, and there will be very little time delay. That is always we want, that we have shown the response, is not it. If I go back, you see our response we look at. For the frequency when I am getting the response here 1. So, that is desirable property. I cannot make the measurement at this region, I want to make the measurement in this region only, right, is not it. So, this will be my frequency response of the operation. So, the omega tau has a lot of influence. Now, if the measurement of high frequency signal is desired, then the system having a small tau will be necessary. Quite obvious is, because our response we have seen again that the response falls down. So, if I want to take the response at the higher frequency, I must use a small value of tau. So, that the omega tau will be, I can accommodate, omega tau will not be large. So, that I can accommodate my frequency in this region, right. A large time constant system will result in the removal of the high frequency component from the output signal. Quite obviously, the output, I mean if the frequency is high, we have seen that if you look at the plot, right. So, that what will happen? That means, I have a plot like this. So, you see here it is falling down. So, that omega tau is large. So, the tau is constant, what will happen? That the frequency component of the output signal, so it falls. If I want to take the reading here, so obviously my output attenuations will be quite large. So, I will not get any output, right. So, that is we are telling a large time constant system result in the removal of high frequency component from the output signal, right. Now, you see that in measurement system, so the first order instrument is even though is not very common, but there are some instruments which you will find first order. But suppose if I take a mercury in glass manometer, I mean thermometer is the first order instruments. In the other way, if we consider that the mercury in glass manometer, then we can consider as a second order instruments. Now, first order instruments and second order instruments differentiations, you will find that, as I told you, that if you look at the output, if we know the output of the systems, and if I can, or if I have a calibrated output in that type of situations, I can tell that what is my output, and if my differential equations I have approximated as the first order systems, I am getting the desired output or the output which is supposed to I get, because if it is calibrated, I must know what is the output. So, I can tell the system is first order. So, if I am not getting, say, I have to go for higher order instruments, for the second order instruments or third order instruments. But in the entire course, you will find that we will concentrate only on the first order and second order instruments. If the system is non-interactive, so I can go for a higher order instrument. Suppose I have a thermometer which is cascaded with a second order recorder. So, in that case, it will be and suppose I have an example I am giving, suppose I have a first order instrument, what happened? I have a first order instrument cascaded with a second order instrument. Suppose it is a thermometer and I have a recorder. So, in that case it will be, if it is non-interacting, I can consider it as a second order, third order instruments. But mostly we will consider these two separately, first order and second order instrument as a whole, as separately. So, this we have considered here in this we have considered the dynamic characteristics of the first order instruments, and these dynamic characteristics of the first order of the instrument, not for the first order, for the second order instruments will be considered in the lesson 3 of this course, industrial instrumentation. This ends the lesson 2 of industrial instrumentation. This is lesson 3 of industrial instrumentation. and we will continue with the dynamic characteristics of a system, especially second order systems. Already we have discussed about the first order system. Now we will consider the dynamic characteristics of a second order system. Now contents of these lessons are the dynamic characteristics, the response of a second order system for step, ramp and sinusoidal input, where we did it for the first order instruments, we will do for the second order instrument. Also, we will solve some problems on the first order and second order instruments. If I look at the ramp input we have seen characteristics equations of a second order system with ramp input can be expressed as follows. Already we have discussed the ramp input in the case of first order system. We are taking same three inputs so that we can compare putting these two side by side. D square upon omega n square plus 2 xi d by omega n plus 1 y equal to k xs dot into t, y equal to dy by dt equal to 0 at t equal to 0. These initial conditions we have discussed this before also. What does it mean? Xs dot might mean my input, it looks like this. This is our ramp input. We have discussed thoroughly this when we discussed the first order system, right? Now this we can do it in the case of second order system. So this is my input, this constant k as it happened before also, xs dot into t, right? So it is a continuously changing with time, so xs dot, so I made it unitless quantity. So these are our initial conditions. Now the last problem you will find is a second order system, so there is no question. So if it is a second order system, you have to take both plus and minus of the dynamic error. That is the reason we have given. So you have to take both. That means you have to take both plus and minus of 6%. So accordingly you will get the value of the omega n. So the natural frequency of the sensors you have to find here. You have to find the value of omega n here. So you try to solve these problems and the solutions will be given in the next class. And I will remind you that here you see that the problem number 3.4, the instrument is first order. Problem number 3.5 also it is a first order system, whereas problem number 3.6 is a second order system. So with this I come to the end of the lesson 3.